So we're still in section 9.2. And we're still interested in series and convergence. So here's what we want to do. We want to express (5.23) repeating as the ratio of two integers. So a repeating decimal, we know that a repeating decimal can be written as the ratio of two integers. A repeating decimal is a rational number. So we want to figure out what those two integers are. So how are we going to go about this?
Calculator.
What do you think, Liam?
Add 5 to 23.
Add 5 to 23 over
99.
So how did you?
99 plus 23.
So how did you come up with 23 over 99? So that's what you just memorize that. So we're going to figure out how we can come up with 23 over 99 as 0.23 repeating. So we're going to start. I'm going to write this as 5 plus, and if I'm going to write this out, I could say this is 5.23 repeating. Let me write it out first before I do the addition. 0.23, 23, 23, 23, etc. So I'm going to write this as 5 plus 0.23 plus 0.0023 plus 0.000023 plus ... So I can write it this way. Now I'm going to change the decimals to fractions. So I get 5 plus 23 100ths plus 23 over 100 squared plus 23 over 100 cubed plus ... Now I'm going to factor out the 23 over 100. So I get 5 plus 23 over 100 times 1 plus 1 over 100 plus 1 over 100 squared plus ... And what do we have here? A series, and it's one of our nice special kinds of series. This is the sum, n equals 0 to infinity, of 1 over 100 to the nth power, or I'm going to write this as 1 over 100 to the n. And we know the sum of this infinite geometric, this is a geometric series. The ratio, our common ratio, the absolute value is less than 1, so we know it converges. So this is 5 plus 23 over 100 times 1 over 1 minus r. And we get that this is 5 plus 23 over 100 times 100 over 99, which is what Liam said earlier. 5 plus 23 over 99, and if we turn this into a fraction instead of a mixed fraction, so 5.23 repeating equals 518 over 99. And we've expressed this repeating decimal as the ratio of two integers. So now we know how to turn repeating decimals into fractions. Repeating decimals we can represent as a geometric series. Isn't that a cool thing? Fancy? This example, it's just such a fun thing to know how to do this, to be able to do this representation. All right, any questions on what we just did on this example? Okay. Let me list some properties of infinite series, and then we're going to talk about a convergence test and another special kind of series. So some properties. These properties, let's listen up, guys. These properties of infinite series come directly from our rules for sequences, because we defined an infinite series as the sum of the sequence of partial sums. So the sum of an infinite series is the sum of the sequence of partial sums. So all of these properties come from the same rules that we talked about for sequences. So we're going to say that the sum from n equals 1 to infinity of a sub n, our sum is a, and our sum for some other series, b sub n, is b. So each of these converge, and the sum is a and b. So our first property that we're going to be interested in is if we multiply each term of a series by a constant, then we can just multiply our sum by a constant.
So could you then, with that one, sort of rearrange it so that you could also do c times the sum of all numbers is the same as, you kind of get it so you can just basically pull any coefficients out
Right.
of the original sigma.
Yes, and just multiply that by the limit.
final number,
Right.
yeah.
Yeah. So the sum of a sum is just the sum of the limits. And our third one is just the difference. I guess we could, instead of writing 3, I'm just going to write plus or minus. We'll do a plus or minus. So those are some properties of series. We can multiply by a constant. We can add the terms together. If we add the two terms together, we're just adding the sum of the convergent series together. And just as a note, that the sum of an infinite series, or the convergence, isn't affected by deleting a finite number of terms from the beginning. So I'm just going to write as a note. Or not the sum, the convergence. The sum is affected, the convergence is not. The convergence of a series is not changed by deleting a finite number of terms from the beginning.
Final sum will change.
The final sum will change, but it's still a convergent series. So we could, if we deleted a finite number of terms from a geometric series, we could find the sum of the geometric series and find the sum of those terms that we've deleted, and then find the sum of the new series. So we can calculate. If we're working with a nice series, that'll allow us to calculate a sum. But the main thing to remember is if we delete a finite number of terms, it doesn't affect the convergence. And that comes up in here and there in things that we'll do and in some problems. All right, questions about this? Pretty straightforward. Makes sense. It's pretty intuitive ideas about series. All right. So the next thing that we're going to talk about is Katie kind of asked about it the other day. Is this test for convergence, and it works one way and it doesn't work another way. So we're going to talk about the nth term test. So first we want to talk about the limit of the nth term of a convergent series. So this is our theorem about the limit of the nth term. So we have a convergent series. So if our series, if A sub n converges, then the limit as n approaches infinity of A sub n, our nth term, is 0. If our series converges, then the limit as n approaches infinity of our nth term is 0. And the proof of this is very, very easy and very short. So we're saying that if our series converges, then the limit the limit of A sub n is 0. So saying this converges means that we're going to say that if this has a sum, we'll call the sum L, that means the limit as n approaches infinity of the sequence of partial sums, because that's how we defined our sum, and I'm going to write that as S sub n, also equals L. So our limit is the sequence of partial sums, so that sequence of partial sums has to have the same limit. I'm going to rewrite this limit as the limit as n approaches infinity of S sub n minus 1 plus my nth term. So I'm just taking one term out of this sequence of partial sums, and then I'm adding this nth term back on. So this, now I'm going to separate this using our properties. This is the limit as n approaches infinity of my n minus first partial sum plus the limit as n approaches infinity of A sub n. Well, the limit of the n minus 1 partial sum is the same as the limit as n approaches infinity, is the same as the limit of the nth partial sum. So that equals L plus the limit as n approaches infinity of A sub n. And since we know that our limit is L, we can't add anything else. So our limit as n approaches infinity of A sub n has to equal 0. So if we know our series converges, we know that the nth term eventually goes to 0. That's what this theorem tells us. Now where we have to be careful, and what you were asking about yesterday, Katie, is the converse of this is not true. The converse is not true. So
what's the name for example where it's not just flips, but also reverse around completely?
we will talk about that in just a second.
I'm trying to remember the word for it.
So the converse is not true. So we cannot say that if the limit as n approaches infinity of a sub n equals 0, then our series converges. So we cannot say that. That is not necessarily true.
If it doesn't go to 0, it diverges, but if it does go to 0,
And we'll get to that in just a second, and that's kind of tied with what Chris said. Does anybody know the most famous counterexample of this converse that shows that this is not true?
1 over n.
The sum from n equals 1 to infinity of 1 over n. You remember what that series is called?
Not harmonic.
It is the harmonic.
Oh, it is harmonic?
And that's our counterexample.
Negative 1, 1, negative, you know.
That's the alternating
It's
harmonic.
alternate series.
So
Okay.
the harmonic series diverges. And that's the sum n equals 1 to infinity of 1 over n. The nth term of the harmonic series goes to 0. The harmonic series diverges. So let me show you a quick proof that the harmonic series diverges. So we have the sum n equals 1 to infinity. This is a nice direct proof. 1 over n equals 1 plus 1/2 plus 1/3 plus 1/4. I'm going to write a bunch of terms. Plus dot dot dot. Now I'm going to write another series. I'm going to write 1 plus 1/2 plus 1/4 plus 1/4 plus 1/8 plus 1/8 plus 1/8 plus 1/8 plus dot dot dot. These two terms are 1/3 is greater than 1/4. Can we agree on that? So this term is greater than 1/2. So these two terms together are greater than 1/2. Each of these terms added together, 1/5, 1/6, and 1/7, are all bigger than 1/8. So these four terms together are greater than 1/2. And I can group from 1/9 to 1/16, and that would be greater than 1/2, and I could keep going that way. So this series is greater than summation of n equals 1 to infinity of 1 over n is greater than 1 plus 1/2 plus 1/2 plus 1/2 plus dot dot dot. And this series, 1 plus 1/2 plus 1/2 plus 1/2 diverges. And the harmonic series is greater than that series. If I group my terms this way, that shows me that. So the harmonic series diverges. This is going to be an important one to remember. This comes up a lot if the harmonic series diverges. Now, what Katie was talking about and what Chris,
Older brother,
right,
years ago.
yeah. What Chris said is, what's the thing when we switch the if and the then all around? That's called the contrapositive. The contrapositive is true. And a contrapositive, and so in logic, if you have an if-then statement, a conditional statement, the contrapositive is logically equivalent to the original statement. So the contrapositive says, and this gives us the nth term test for divergence. So this is a test that shows that decides whether or not a series diverges. And our nth term test for divergence says that if, I'm going to switch it around, if the limit as n approaches infinity of a sub n does not equal 0, then the sum from n equals 1 to infinity of a sub n diverges. So I switched my if and then, and basically I put a not in front of both of them. And that's a contrapositive. Change the order and put a not in front of everything. So this gives us a test for divergence. If our nth term, as n approaches infinity, if our nth term does not approach 0, we can conclude that our series diverges. But it's always very tempting to argue that our nth term approaches 0, so our series converges. And we cannot do that. Questions? All right, I have a couple of questions for you. If a sub n equals n plus 1 over n, my question is, does the sequence a sub n converge? So let's think about it for a second. Does the sequence a sub n converge? The sequence converges. The sequence converges because as n approaches infinity, a sub n approaches what? 1. So the sequence converges. How about, does the series converge? So our sequence converges, does the series converge? No? And why not? So our sum, our nth term, not our sum, our nth term as n approaches infinity is 1. That's not 0. So the answer to this is no. By the nth term test. All right, a couple more questions. What is the difference between these things? I'm going to write down 3 things here. N equals So what is the difference between those 3 things? Anybody want to give an opinion? So let's look at them one at a time. What's the first one? It's just a sum. It's just a series, right? How about the second one? Yeah, the same. We just had a different name for the letter that we used to index index our terms. So the first two are the same. How about the third one? What is this third one telling us to do?
Some of something defined by K,
Yeah, it's some,
but
I think it's one different, you have something really defined in terms of K.
Right.
So it would be, unless maybe so, that's the way choosing from the
Okay. So what Liam is saying is ace of K is just some number, right? If they give you, if they say ace of K is 10, this is telling me to sum 10 an infinite number of times. So this is just the sum of a constant. The A doesn't change, my terms don't change as I index my sum. So this is just ace of K plus ace of K plus ace of K dot dot dot. So we're just adding this constant together an infinite number of times. So if ace of K is some finite number, the sum is going to be infinity. If ace of K is 0, then our sum is 0. So this is just a sum of a constant. So we're just playing with the indexes here, indices. All right, any questions? So it's important to keep that nth term test straight. The nth term not approaching 0 tells us that a series diverges. We can't assume if the nth term approaches 0 that the series converges, because the harmonic series are harmonic series that are counterexample. The harmonic series diverges. And we also have a nice way of figuring out rational numbers from repeating decimals. Okay. All right, there you go.